for where you can get the material. So please use the opportunity, the 10 minutes, the registration form. I've already shared, but I can share again. Please stop sending information on the chat so that you can receive the Google link. There it is. Oh, okay. Let me check. Thank you very much. I was sharing only to panelists. There you are. I'm going to paste it twice. Then I'm also bringing the registration form for day 4 and reshare it. That is registration for day 4. So please pick it, click on it and register for day 4. The link for the information that we've been using from day 1 to day 4 has been updated. So download in 10 minutes. Then Dr. Thomas will join you and redo some of the bits for yesterday since people are already tired. But make sure even when you look in the folder for day 3, there is an updated version of the PowerPoint that you were asking for yesterday that Dr. Thomas used for presenting. So look through, you will see it in day 3. Then there's also material for day 4. Thank you very much. I'm giving you, now let me go off at 10:10. Dr. Thomas will come in. Thank you.
Hello, good morning, everybody. I hope you had a good night and fresh enough to start the day. I would like to continue from where we left yesterday. And I'll try to, so what I want to do is to just try to briefly look at the, first try to remove this thing is, I want to look at how we use R to generate randomized complete block design. So I yesterday told you that we first get myself as a pen with a color. Today I'm going to use green color. So we started with setting the seed. And yesterday I explained that the reason as to why you set the seed is because you want to repeat. If you want to show the same randomization again to somebody else, then you need to set the seed and you get the same thing. Otherwise, if you don't set the seed, then every time you do the randomization, you get a different thing. So this allows, so I told you yesterday that this sign here will tell Ara that please, whatever you find after this sign is just my comment, don't bother to run it and don't show me that is an error. So the first thing that we've done is that we have 3 treatments here, and let's say we want to replicate each one 4 times. So that means in total, I will have 4 A's, 4 B's, and 4 C's. That means I will have a total of 12 observation, 12 treatment points that I need to. So I need 12 experimental units. So what I'm trying to do here, are you getting me? Hello? Am I? Okay. Thank you. Okay. So what we are doing here, we are creating a vector called F, and that vector called F, we're going to make it a factor, and we say we make it a factor because a factor categorizes. So you either belong to group A, group B, group C. And this is going to be very important, especially when you're going to do analysis of variance where you need factors. Factors are different from, you cannot make a quantitative variable factor unless you divide them into different category, like Ellen was talking about in the first day. So here we're creating F, which will have AA 4 of them, BB, CC 4 of them. So this is the simple command that is used there. The next thing then is we're actually going now to do our randomization process. So the randomization process is simply, we are saying we have our experimental unit up to 1 up to 12. We want to assign treatment to them. So the first thing we're going to do, we're going to start by, we're going to do from F, which are 12 different observation. What determine the seed? You just put any number. What you want is you just want to be consistent that if it is 10, you put 10, then next time you repeat the same thing. Don't worry about how that is generated. For now, it's not very relevant. Thank you. So we create, so this is actually the actual randomization process. So we're saying from our 12 observation, pick the first one and give it to plot number 1. Pick the second one, give it to plot number 2. Once you pick, please don't put it back. So here then, after we've done this, we get some result. You can actually observe the result that you have done. The next thing then would be to create, we want to level our experimental unit from 1 up to 12. And then we want to create some kind of a data frame. And in that data frame, the first column, we want to have our experimental unit. And then in the second one, we want to have our treatment. That is which, so we're saying in the first experimental unit, so this 1, 2, 3 up to 12 is this part here. This is the part that is giving it there. And then this A, B, C, D is what we sample here. So it is this part here that is responsible for that. So here you have your, so then I can go and say, well, for rat number 1 will get B, rat number 2 will get C, rat number 3 will get A, and so on and so forth. So that was the generation. We already talked about this, so I'm not going to repeat this. Okay, so maybe just to reemphasize some points, when we assume that the experimental units are homogeneous, then any variation that is not taken care of by the environment, by the treatment, will be lumped together, and this will be what we call experimental error. So we need to be sure that whatever is lumped together as experimental error does not have any other pattern apart from experimental error. So from here you can see that the values are quite similar, and when you calculate the variance is actually quite low. Now, when you come and look at this side of the illustration, you find out that in addition to receiving the same treatment, we also see that the animals themselves are different. So there's going to be differences that would occur just naturally for if the experimental unit were uniform. And then there's also variation that is as a result of the differences between the different experimental units. So you can see that has resulted into a high variation. Now, as I indicated yesterday, when you're doing hypothesis testing, this variance here, the experimental error variance, is the one that is used as your denominator for calculating your statistics, whether it is a T statistics or an F statistics or chi-square statistics. You always have variance included. So the implication would therefore mean that if you don't design your experiment very well, you're going to have a lot of noise. And once you have a lot of noise, then you will not be in position to detect any signal. It's the same as if you're in a noisy place. Let's say, for example, you go to a bar and then somebody calls you. Of course, the signal that comes from the phone will remain constant, but your environment will determine whether you're going to pick that signal or not. So if you're in a very noisy environment, you will not pick the signal. Not that the signal is not there, but the main reason here is that you're in a very noisy environment, and therefore for you to pick the signal, you need to get away and move away from the source of the noise. And this is exactly what we do when you are designing your experiment. You need to try to minimize the source of noise as much as possible so that you only remain with noise that you cannot avoid. And that comes from the fact that experimental materials are different. So you can see if you're an animal scientist, you see on the farmer's field, there are all sorts of animals. So you can have animals as the macheted animals, you can have with very good body conditions, you can have animals with long horns, you can have animals with short horns, you can have animals without horns. And this in one way or the other may actually affect the response of the experimental material to your treatment. And that response, that effect of the experimental material on the effect of the treatment can constitute part of the noise in your experiment. So you need to make sure that you minimize as much as possible. So this brings us to a second design, that's what we call randomized complete block design. So here, of course, we now assume that our experimental units are not homogeneous. The other assumption is that there is a predictable trend in the variability in experimental material. So you can, if you are doing experiment in the field, for example, oh, the video has stopped. But you're seeing the screen, right? I think I minimized something. Yeah, that's okay. So what we have here is that I think this particular line is very important to me. That when you go to design your experiment, you need to have a full knowledge of your experimental material. So if you're going to do a field experiment in area that you've never been there before, it's important that you pay a visit to the field, you try to mark up some features that will help you in your randomization process. So in randomized complete block design, we assume that your experimental unit can be put together in what we call blocks. And then we want to see that within the block, the experimental units are similar as possible. And then we expect variation between the different experimental blocks. Now, if you block just for the sake of blocking when the experimental units are not homogeneous, there is a cost that is going to be associated with that. So it's not you're not going to get away with it. So in the field, you could have something that looks like this. So let's say you go to your field, maybe you do soil sampling and you come out with something that looks like a map of your field. So we seem to see that the plots get darker in terms, let's say the soil get darker in terms of color as you move from point A to point B. Okay. So what we need to do therefore is that we need to actually identify plots or pieces of land or a portion of the land that you think are similar. So we can actually say, for example, that this part here is actually similar in terms of, say, soil fertility. And then you look at this as being another part that is similar in terms of fertility, and so on and so forth as you go. So you can see your plot number 1, plot number 2, number 3, number 4, number 5, number 6. So these plots here, we assume that they are similar because they're having the same fertility. But if you look at this other plot here, let's say this is number 36, number 35, 34, number 33, number 32, and then number 31. Okay, so if I have treatment A here and another treatment A there, the difference between the value that I receive here and the one I receive there is partly due to experimental error variance, but also partly due to the fact that this one here is less fertile compared to what we have there. So that is why we do the blocking. So the blocking will enable us to actually reduce the noise. This is the same as you getting away from where there is noise in a bar to go a little bit at a distance so that you can answer to your sweetheart and tell them whether you love them or you don't love them, because you might be telling somebody I love you and another person is saying no from the background, and then you send out a wrong signal and you will not be able to get exactly what you're looking for. Okay. Then I yesterday also showed you how you can generate a randomized complete block design using R. So the first method that I showed you yesterday does not require any program. It's just a simple creation of you create your treatment. So here we have our treatment A, B, C, D, E, and F. These are the treatment that we want to assign to the different plots here. Plot 1, plot 2, 3, 4, 5, up to 6. So what we're going to do is, the first thing we're going to do is we're going to look at block number 1. So we assign our treatment, we do the randomization block by block. So what I'm doing here is I'm saying, okay, this B1T is how do I assign my treatment in block number 1? So I get my treatment, which is A, B, C, D, what I call treat here. I say sample 6 of them, okay? And the sampling here, it means I'm going to sample without replacement. So that means if I picked B for plot number 1, B will now be removed away from my pot. I will have now the remaining one, then I pick the next one, and so on and so forth. So the results of this, for example, will give us this arrangement here. So what happens here is then that we're going to pick the first one for plot 1. It becomes C. So after that, Now we only have A, B, C, A, B, D, E, and F. The next one we pick for plot number 2. We remain with the D, B, E, F. We pick for this, we pick for that, and then the remaining one now will automatically come for that. Then after you're done with that, you move and then do randomization for the second step block, which is this one here. Then you do for the third, you do for the fourth, you do for the fifth, and then you do for the sixth. These other commands here, this is just simply to put your observation together so that you can get some kind of a matrix that is easy to observe or you want to print. So what I've done here is I'm creating now a new object called treatment, and that object there as the component, what I assign in block number 1, what I assign in block number 2, what I assign in block number 3. Okay, and I've written here, same, create a combined vector of the treatments in the different blocks. Then the next thing I do, I also want to create another object called block. And the block is also going to be, I'm going to have block 1, but I'm going to replicate it 6 times so that I can have this. This is block 1, block 1, block 1, block 1, block 1, block 1. And then I create a plot, which is 1 to 4. Okay, no, I think this should be okay. Okay, so this one is, we are creating another component here, another object called plot. And this one I said I have replicate 1 up to 4, replicate 3 times. And then here, what I do now is I have plan. Now I'm trying to create this data frame now, like the one we have before, so that this is what you want to carry now on your paper and you go with it to the field. And then after that, I print. When you type something in R without mentioning any command to it and you enter, it will print for you the value that one has. So this is what the result will end up. We end up with some kind of results like that. But I also told you yesterday that this very important library called Agricole, this library here can sort you out if you are working in agricultural research or if you're doing things that do with analysis of variance. This is one of the packages that you actually need to do. Now, of course, you need to install this package before you can call it and using the word library. And then once you call it, then you should be able to do the analysis. So it's still the same thing here. I need to create a vector of my treatment. So this time I said I have 6 treatment 1, 2, 3, 4, 5, 6. And then this is actually the actual command that do the randomization process. So within the Agricole package, there is a function called design.rcbd. So RCBD here means randomized complete block design. So you have design.rcbd, there is design.crd, there is design.lsd, there is design.split. So I can use that to generate. So here, what we're saying is that these are my sets of treatment that I want you to randomize, and I want you to put it in 6 different blocks. And then I'm also say here that in case I want to repeat this process, let me set my seed number to 11. So if all of us set the seed number to 11, we should be able to get the same results. Okay. So once we are done with this, so we run this command here, design.rcbd. It will give us something that we will assign it to that. Okay. Now this out.design is also an object, but this object has a lot of things in it. So what I'm going to do now is I'm going to first stop sharing. I'm going to go to R, and then I'm going to run something, and then I show you what is in that, what is the content of that out.design. Once I run that, and then I will tell you why we have this particular thing here. So let me first clean it up a little bit. I need a eraser here. Okay. So let me stop sharing or share a new one. Okay, so are you seeing my screen well, or I need to enlarge a little bit? Are you seeing my screen well? Can I see some yes or some no's? Okay, good. Okay, so what we have here is, I told you can run this without any problem. Once you open it on your computer, you don't need to do anything to actually run this. You don't need to go to any folder. You don't need to do anything. So we can just run this briefly. So we set our seed. We have created our factor. Let me just type so I just typed F, sorry. I typed F here on the console. I ran it. So this is what we have created. So remember what this thing is saying is that I have A, B, C, and it says each should be equal to 4. So you can see here, these are 4. The next ones are 4. The next ones are 4, making a total of 12. And because we called it, we made it to be a factor, so then it tells you that we have levels A, B, C, because factors have levels. Okay, so the next thing that we did was we did the sampling. So we have this object here, FAC, which we can actually see what it is by clicking on that. So you can see this is what we have. So in the first rat, for the first rat, we got B. For the second one, we got C. For the third one, we got A. For the fourth one, we got B. For the fifth one, we got A, like that until the 12 rat. Now, what we are creating here, now we want, with this command here, you see 1 to 12, we're just creating, we are just creating a vector with the 12 observation running from 1 to 12. Let me just print what it is and you see. If you only want to take a small part of the command in your RStudio, you highlight it rather than putting the cursor on it. Once you highlight, then it will only run that small part there. So you can see now here I have 1, 2, 3, 4, 5, 6 up to 12. That's what I've just generated. So what this plan does is then to say, well, I'm going to create a data frame. Ellen talked a lot about data frame on the first day. Data frame is your data set. And then in the first column, I'm going to have this 1 up to 10, 1 up to 12. And then my treatment that is assigned to the different unit is going to be in the second column. So I click on this, and then I can print and see what it is. I highlight there, I print. So this is what we saw. Now, if I go ahead and change, let me try to change the seed. I change the seed to say 100. Okay, I run this. So let me print the plan, the plan. So you can see now we have a C now instead of a B. Okay, so if you change the seed, you're going to change. So every time you change the seed, you're going to get a different plan. That's why I say if you want to go and you want to generate it to somebody else and you want to say this is the one that I use, then you need to keep the seed. Okay. Oh, I got myself a different. Sorry, I got myself completely a different script, so I got a bit of a mess up. So I'll get it for you. So let me first change the sharing and go back to the screen. I'll organize it and get back to you. Okay. Okay. Just hold on a little bit. Let me look for the. I think I can go and get it from the link itself. I want to get this link. So let me get the link to day 3, day 2, 3. Okay, this is. Okay. So are you seeing my screen? Are you seeing the ARA, my ARA studio? No? Yes. Okay. So I got my command here. So the first thing is you need to install the package Agricole. I already have mine. So what I'm going to do, I'm just going to click run. And then I'm going to look for, I want to illustrate something. Okay. So here I have my command. Don't bother so much about the different parts. Okay, let me do like this. Treat. One to 6. I also get to get red, so don't worry. Okay, so what we have here, this is what we have generated from the design. So what happens is that we can look at the structure of this particular object that we have created. Let me clean my screen a little bit. Okay. So what I'm going to do, I'm going to look at the structure of RCBD. Okay. So you see from here, it tells you that this is a list of 3, okay? And on the first list, it has parameters. So under these parameters, they tell you the design, which is RCBD. It tells you the treatment, which is 1 to 6. It tells you the number of replicate, which is 6. It tells you the series, which is 2, the seed, which is 11, the kind, that is the kind of randomization. It said is super duper, and then it tells you whether it is logical, true or not. Then the second on the list is the sketch. So the sketch now will give you kind of the sketch of the field or the plot that you want to. And then the other one that it gives you the book. Now the book now is the one that has some kind of a data frame. It has 36 observation of 3 variables. So what we can actually do, so if we want to extract any of these values here, we use the $sign, as you can see up there. So I can have my RCBD. It suggests for me. So what I can do, I put the $sign. Then as you can see, you see the 3 different lists will come. So if I get the book one, then it will actually, this is what it gives me. You see, the book is a data plot. So it tells you plot 1, 0, 1. So instead of counting from 1, it counts from 101, 102, 103, 104, 105, 106. So these are our plot 1 to up to 6 in block number 1. And this is where your the different treatment that you need to put there. So on plot 1 in block 1 is going to be treatment number 4. Treatment number 6 will go to plot number 2. Treatment number 2 will go to plot number 3. Treatment number 3 will go to plot number 4. Treatment 5 will go to plot number 5, and then treatment 1 will go to plot number 6. And then when you go to plot the second plot, you get the same thing and go on. So I just wanted to show this why we have this. So you can see from here, I'm creating another object called RCBD. That RCBD is going to be one of the lists that I have in the output of the design.rcbd. So as I say, I'm picking one element from a list, and then the command here we are seeing here is a simple one. We are saying you level the blocks. Remember here our block is written as 1, 1, 1, 1, 2, 2, 2, 2, 2. So I'm trying to tell Ara that level for me the blocks as block number 1, block number 2, block number 3. So we can run this. We say RCBD, which is, we extracted this data frame. We are going to level it, and then we are going to print to see what it is. It should then give us change now. From 1, 1, 1, 1, now we have, so you can see from here now we have block 1, 1, 1, 1, block 2, 2, 2, 2, block 3, 3, 3, 3, and so on and so forth. So this one here, you just need to print on your piece of paper, go to the field, start the work, and you're done. Okay. Life is quite easy with that. Any question? Anything that you think I need to address from the chat? Okay. So now let's go and look at our second design. No, not the second, the third one. Okay. Oh, this thing is teasing me properly. Okay. So we're going to look at the third type of experimental design, what we call Latin square design. If you happen to be a Luo speaker like me, This one it means the child, but this is a different thing here. So here, when we looked at our randomized complete block design, we saw that we are controlling variation in only one direction. But with the Latin square design, we are controlling variation in two directions. So with RCBD, let me get a pen. So with RCBD, what we've done is that we are controlling variation in this direction. And please, your block should run perpendicular to the direction of the blocking factor. So your block should run this way if the factors run this way. Otherwise, you're going to line them in the wrong direction, and then you're going to compound and make the problem a lot more bigger than you'd have. So let's say, for example, here we go and realize that there is a slope in the land that we are using. So it's running from this point going that point. So this is the lower part of the slope. This is the upper part of the slope. And then we also realize that there's some kind of fertility gradients going on, that this is the lower part, the lower fertility on this side and upper fertility on that side. So from here, you can actually see that you have two different directions. So here you can see that you have, if we look at this part here, okay? So what we can see here is that this block here will be on the lower slope, and this block here will be on the upper slope. Okay, we have in the middle and that. So in that case, we have a randomized complete block design. We have a randomized complete block design when we are looking at this direction. Okay. Now let me change the color of my pen to my favorite green. But when we look at the fertility, we were going to see that these plots here are actually on low fertility, and this plot here on high fertility. So in a way, now we have two variation that we are dealing with. We are dealing with variation in the fertility gradients. We're dealing with variation in the slope gradient. I think I presented somewhere like this. So here you could have, let's say we have some trees here. So it is shading. So here you have high shading effect of the tree. We have low shading effect of the tree, and then here we could be having fertility. But this is, you can make this to be as one part of the this one should overlap, and you have two different. So you, in other words, you have two randomized complete block design together. One using row as a blocking factor, the other one using column as a blocking factor. This is also used frequently in laboratories where let's say you have different machines, and then you also have different operators or technicians. So here we have 4 machines, machine number 1, number 2, number 3, number 4. I have operator 1, operator 2, operator 3, operator 4. So here you can see here that operator 1, okay, so we are blocking by operator. This is operator 1. We have operator 2. We have operator 3. We have operator 4. So as far as operator is concerned, we have randomized complete block design because the blocks are complete. All the treatments are there. Okay. Now we also have different. Let me change the color. So, but if we look at machine, we can also block with the machine. So machine 1, machine 2, machine 3, machine 4. Okay. So here then you have your, these are what called the rows. Yes. We have the rows, row 1, row 2, row 3, row 4. And then here we have column 1, column 2, column 3, column 4. So this is why we call Latin square row column design. You look at controlling variation in terms of rows and in terms of columns. It's also used frequently in animal science, where you can look at, let's say you can even look at lactating animals. So yeah, you have animal number 1, animal number 2, animal number 3, and then this could be the lactation period 1, period 2, period 3, period 4. Remember here, this animal here, so this animal here received the different doses of medicine in a different period of time. So we can control, we can block using the animal, and then we can also block using period. Remember, the animals may differ in terms of their body score conditions, in terms of breed, in terms of what, but the period also differs. The first period of lactation has a different characteristic to the second period of lactation, third period, and so on and so forth. Okay, so Latin square is laid out in row column. So sometimes it's called a row column design. But what we have is that whether you're looking at from the row or looking at from the column, each of them is a complete randomized complete block design. So here the key characteristic here is that the number of replication is always equal to number of rows, equals number of columns, equals number of treatment. And this is why we say it is a square, because the row and the columns have equal numbers. So the total number of treatment here is actually the square. The total number of experimental unit that you need is the square of the number of treatment. And this is where the challenges come. For field experimentation, the challenge comes in. If I have 10 treatments, that means because the number of treatment is equal to number of replication, that means I need 10 replication. So if you're dealing with the plots of land, that means you need 100 plots. Okay. Now these 100 plots of yours, I don't know how you're going to arrange them so that you get your nice thing, because then it will become extremely big. So in most cases, beyond 9 by 9 Latin squares are not used in field experimentation unless you use half square. You cut part of the square off. So we're going to see some row column design under incomplete block design. That actually you don't have a complete square either on the row or the column, you reduce it a little bit. So here, so by blocking in 2 directions, we assume that you reduce the experimental error compared to when you're using just RCBD. So I talked about the limitations of that. The square requirement is provide limitation for large experiments. So if you have 20 treatments, that means you need 400 experimental units, and in the field this can be extremely large. If the field is very, very large, there is no longer guarantee that within a block you're going to have uniformity. So if you have a block that is say 500 meters long, it's very difficult to assume that a plot at the beginning of the block and the one at the end of the block are going to be uniform. The other challenge with the Latin square is that if you have 3 or 4 treatments, then you will have very few experimental units. So it becomes inefficient because the degrees of freedom for the error will be quite low. And then we have several incomplete Latin square design. They're called Youden squares that I'll say something briefly when we come under incomplete block design. So just like we've done for RCBD and for CRD, we can also generate a Latin square design in R. So here I'm going to explain what happened and I'm going to run for you. So here we are creating an object called nutrition. And this object called nutrition is a vector with the 5 elements. Now, somebody was asking, yeah, why do we put a quote on this, because now this is kind of a character. These are characters. So we are looking at this, we're considering this as one thing. So it doesn't matter how long it is. We take it as one point. So here, this is going to be nutrition 1, nutrition 2, nutrition 3, nutrition 4, and nutrition 5. Okay. So we go back to our randomization. We're using, so this time we're using design.LSD. So LSD means Latin square, not least significant difference. Say block number 2 and the rest. Probably it's a typing error. Okay. So this is, remember, for RCBD, we had design.RCBD. And here we have design.LSD, which is least Latin square design. So remember, this nutrition here is what we created up here. And then we have our seed number there. Okay. And then after we have designed, we want to extract element, a list book from our output. So we have the $sign here, and then we level. So we want to say levels for the row of the Latin square should be leveled as week 1, week 2, week 3, week 4, and week 5. Then the column should be leveled as animal 1, animal 2, animal 3, animal 4, animal 5. So what we are doing here, we are simply leveling. And then my good friend Ellen talked about the head. If you say head, I mean, give me the first 6 rows of this, what you've created as LSD. So this is what we have. So you can see from here, we have plot 101 in week 1, animal 1, nutrition 1. Okay, that is what the randomization. So the first animal in the first week will receive nutrition 1. The first animal, the second animal in the first week will receive nutrition number 4. The third animal will receive nutrition number 2. The fourth animal will receive nutrition number 3. The fifth animal will receive nutrition number 5. So this is our week 1. Then you go to week 2, week 3, and so on and so forth. So I want to run this. The treat function. No, the treat function is a vector that we have created. It's not a function, it's an object that we created. Yeah, so it's just a list of, it has the elements that treatment 1, 2, 3, 4. Any other question? No, forget about the super duper for now. I'll show you what, if you want to know about super duper, I'll show you. Okay, let me just change a little bit and go to another one. Yes, you can print, but remember exporting. Remember Ellen talked about exporting. So you can write it in Excel, okay? You can write it in Excel and then you save it, then you actually get it later on. But it's also, it will actually be the beginning to your data collection, how you can develop your data collection form now. Okay, so let me just clean. I'm going to answer you the super duper thing. I'm going to answer you by showing you the source where you can get it from. Okay, so Ellen talked about the help function. Okay, if you want help, another way of doing it, if I put a question mark and then I say design dot CRD, Okay, you start by putting a question mark, design.crd, and then you just enter. So I hope you are seeing on this side of the, okay, what we have here, it's telling us that design.crd, it is in the package Agricole, and it is called, the title, the whole thing is here, randomized complete block design. And then it tells you it generates completely randomized design with equal or different repetition. Random uses the method of number generation in R. The seed is set by set.seed, seed kind. So here then what it does is it shows you how you can use it. So you said, okay, what you do, you type your design.crd, and then you need an object which we call TRT, what I put mine as treat or as nutrition. And then here you need R, you need series, you need seed, and then you say you need kind, you need randomization is equal true. Now, so typically, if you want to learn R, you need to use the help command a lot. You see from what happens here, from here now, you go down, they give you an example, okay? So you can actually start by running this example. With this example, if you copy it correctly, you will never get an error, okay? So you copy this one here and then run it. Then it becomes easy for you to say, okay, now treat actually is you create this. So now what you do, this one you put your own treatment now. Don't try to copy the treatment of these people now. Put your own treatment. If you have 5 treatments, you can say variety 1, variety 2, variety 3, variety 4. And then here you're creating how many replicate you want. You can see from here that for this one here, we want four replications. For this one here, we want 3 replication. How many treatment can a design handle? As many as you have, but then you need to choose an appropriate design. Okay, we are going to talk about, I mean, as we are going to talk about, I talked about the block as the block being complete. By block being complete, it means I can have all my treatment in a given block. We are going to see in what we call randomized, for what we call incomplete block design, that sometimes if you have very many treatments, then they may not fit into a block. So your block are going to be smaller than the number of treatment. So this choice of your experimental design will depend on a number of things. The first thing that we talked about, what assumption do you make about the characteristics of the experimental unit? If the experimental units are homogeneous, if, for example, you're doing experiment in the lab using test tube, for example, you can handle as many treatment as you want, and as many replicate as you want, as long as you have enough test tube to do that. Okay, but if you're going to the field, things will change a little bit. It will depend now entirely on if, like, plant breeders always have a lot of treatments. I mean, you have maybe 200 varieties. So 200 varieties cannot fit into one block. So we are going to see that you can actually have blocks that have fewer experimental unit compared to the number that you have. You promised to start with CRD. You're forgotten. Hey, I started with CRD, no? Can this person be a bit clear? Hey, I started with CRD. I think probably, maybe I didn't make it clear that I was starting with CRD, but we will always come back to certain things, please. Okay. So here you see, in this case now we are actually having different number of replications for the different treatment that you have there. And then, so what you do is simply get this, put it in on your script, and then run it. And that's how you actually learn how to use R. Okay. So I think the issue of super duper is going to be defined somewhere here. So this one tells you R is the replication, series is plot 1 to 11, plot 2 to, so this, when you put 1, then you're running them into from 11, like 1, 1, 1, 1, 2, so and so on and so forth. If you put 2, then you run from 10, 0, 10, 1, 10, 2, 10, 3. If you put 3, then what is telling you now is where do I put the plot number? Is it on the first after the ones, or after the 10th, or after the 1,000? Okay, but this really is quite irrelevant in a way. This is just how you want the numbering to be done, so you don't need to worry about that. So the method, the kinds here is, they tell you the method of randomization. Now the method of randomization, you need to go and read, and here they also give you, so they give you that these are the possible that you can choose. You can choose this one here, Wichmann Hill. You can use Massaglia. You can use super duper. You can use this. You can use that. So what this implies is that after this, you need to go and read and find out exactly what these ones here are for. Okay, and then they also give you the values. Will have parameter, design parameters. You have field. You see the book. The book, I said that is what called the field book. So if you are a field person, then you know exactly what we are talking about here. And then, so the author here is Felipe. This is actually the gentleman who designed the Agricole. I think it was part of his MSc work. And then they give you the reference also. And then there are also other like design.ab, design.alpha, design.bib, design.split. So you can click on this, then it also takes you to where you have, okay? So I'm going to repeat this. If you want to learn R, you're not going to wait for somebody to do it for you. What we have done here is actually enough to make you become an expert in R if you want, okay? Otherwise, you're going to attend 10 courses and you will never be perfect in R because you just don't want. Okay? I hope I've made my point quite clear. So we can have the whole LSD. Okay, I'm not run this. So this one shows the top, but I can show everything. If you use tail, then you show the last six. Okay, so this is the whole thing is here. That's one. If you have 10 treatments and dealing with 20 fish, can I use Latin square? If fish is your experimental unit, if you have 10 treatment, then you need 100 fish. Okay? Yeah, because it's the number of replicate is equal to the number of treatments. So that means you need 100 experimental units. Okay? So why would you want to use the Latin square with fish? Unless you say each fish, okay, you have 20 fish, then you need also to make observation and 20 time points. So you have 400 experimental unit that you need to have. Okay. Okay. So the next thing that we are going to look at, I'm going to go back to. Are you seeing the PowerPoint now? Okay. They are not, okay. 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 So what we have here is then that we ran our Latin square, and this is what he has given us. So with the book now, you can actually go and carry out your experiment without any problem. The other design that I want to talk about now is what we call a split plot. We always put the design in the split plot in quotes to show that the splitting is more about how you lay out the treatment. It's more about the treatment arrangement and not really how it's not a design per se, because what happens that you can use split plot with CRD, with RCBD, or with Latin square. So it's more of treatment arrangement than design. And this is mainly used with what we call factorial experiment. So can somebody tell us what a factorial experiment is? What is a factorial experiment? I'm in the chat to see the responses. You have two or more factors. Repeated experiment. A factorial experiment is one when you have experiment which have more than one factor. Experiment with more than one treatment, many variables. Multivariate experiment, more than one treatment. Many treatments. Now, what is treatment? What is a treatment? What is a treatment? Okay. Let me now first. Oh, thank you for the answers. Okay. So let me just briefly. So treatment are what we're trying to test. Okay. So let me just give an example. Let's say we're looking at varieties of maize, for example. So we can look at say variety 1, variety 2, variety 3, and say up to variety 6. Okay. So each of these is a treatment. We are seeing the effect of each of these. But all these ones here together, they can be categorized as variety. Do we agree? Okay. So a factor is a group of treatment that are similar. So here we have 6 different variety, so we can call them as factor variety. Okay, so you can see from here is that we have 6 different varieties here. Okay, now we also have in this same experiment, we have where we spray, no spraying, versus spraying. Now, these two together is associated with spraying. So these two are similar, so they become a factor. So a factor is simply a group of treatment that are similar or the same category. Like for variety 1, 2, 3 up to 6, they are a group of varieties. Spraying, no spraying is groups of spraying method or whatever you want to call them. But so each of these, if you're looking at variety alone, each of them constitute a factor, constitute a treatment, and for spraying, each of these constitute a treatment. But if you're looking at these two in the same study, then we have combination here. So we have variety 1 with spray. We have variety 1 with no spray. Then we have variety 2 with spray, variety 2 with no spray, until you have up to variety 6. So how many combinations do we have? How many combinations of variety and spraying do we have? We have 12 combinations. That is 2 times 6. Now, each of the 12 combination is also a treatment. So this is our treatment number 1, treatment number 2, treatment number 3, treatment number 4, up to treatment number 12. Now, a treatment is certainly the final thing that is going to end up on a plot or on an experimental unit. So when you are doing an experiment in which you have 2 or more factors together being studied together, then that experiment will qualify to be a factorial experiment. But there are different versions of factorial experiment. So the simpler one that we are dealing with is the one that has all the possible combinations. So here, what we would say, we have a 6 by 2 factorial. 6 by 2 factorial. Okay, so now I've defined what factor, what treatment are, so I can go back to my split plot now. Let me first rub. Okay. Okay. So yeah. Okay. So here is split plot. When you see split plot, you know that you're dealing with a factorial treatment structure. That is the first thing. And in most cases, what happens is that one of the factors probably require a larger area for application and compared to the other. So there are things like, for example, if you go and look at method for cultivation. So if you're using a tractor, for example, as a method of cultivation, it would be very difficult for you to use a tractor to plow a 2 by 2 meter. Okay. So let's say here we have a block. And this block here has different plots. Okay, so let's say we are testing 3 methods of 1, 2, 3, 4, 5. Let's say we are testing 5 methods of cultivation, of tilling land, and one of the method is using a tractor. Okay, so let's say this is 2 meters by 1.5. Okay, so let's say when we are assigning our treatment somehow, it happens that, let's say it happens that this plot here is supposed to be plowed using a tractor. Okay. This one here is supposed to be plowed using hand hoe. And this one is supposed to be plowed using a tractor with another implement, a tractor plus something else. Now imagine that you're going to plow 2 meters here, 2 by 5, 1.5 meters, then skip and come again and plow here. You're going to find a lot of challenges actually implementing your treatment, which is plowing. This is also the same with application of irrigation water. So in some cases, you may need a bigger experimental unit for some treatment, and while the other treatment may need a smaller experimental unit. So in most cases, split plot design is used mainly for logistic reasons rather than for its own efficiency, although some people describe it as super efficient in one way or the other. Now, as I indicated before, that a split plot can actually be used with CRD, can be used with RCBD, can even be used with a Latin square. And this one we're saying is more of a treatment arrangement than a design in itself. So what happens here is that we have 2 different factors for split plot. So we need a bigger plot, a bigger size of the experimental unit for one of the 2 factors. So we need to split the experimental unit into we need to first split it into a larger experimental unit, and then split the larger experimental unit into what we call a subplot. So the first thing that we do here is to, let me just create a new page first, and then sorry. I'm doing this for those who have not seen it so that they can. Okay, so I just want to use this as a blank to draw. So what we have here is that if, for example, I have, okay, I have my pen there. So let's say, for example, here is, I have a plot of land. Okay. Now, because my spraying is one of the treatment that I have, because my spraying requires a bigger area. So the first thing I'm going to do is I'm going to say this is my block 1. I'm going to divide my block into 2 parts, and these ones are bigger units. So this unit now, I have my spraying and no spraying. So like we did before, we are going to randomize this here. So let's say, for example, that spraying falls there, and then non-spraying falls there. Okay. Now we still have our variety. Now, what we are going to do in this case is we have 6 varieties. So what we're going to do, we are going to come here where there's spraying, and where there's no spraying, get another color. Okay. So we're going to split this one up into 6 different pieces. 1, 2, 3, 4, 5. Okay. So the bigger plot here, what we call the whole plot, is going to be sprayed, but the subplot is going to have different varieties that we have. So you can have your variety 1, maybe variety 5, variety 4, variety 3, 2, variety 3, and so on and so forth. Now, of course, what will happen is that you're going to plant your maize here, and then you come and later spray this one up together because spraying will require a wider area. You come and do the same thing here. So the splitting is what we're saying, that we have a big plot, which we call a whole plot. And then from the whole plot, you get subplots. Yeah. Replication is part of all designs, okay? Whether you're dealing with CRD, you're dealing with RCBD, you're dealing with replication simply means that each treatment or treatment combination in this case has more than one experimental unit receiving it, okay? So that is what that's what the splitting is all about. So the first thing is you get your block. If you're using it in randomized complete block design, we divide the block into 2 larger blocks, plots, which we call the all plots, and then we randomize within this. So here then you have no spraying as one replicate here, no spraying as another replicate there. Then we come and then split this one into 6, split this one into 6, split that one into 6. So then you have varieties now imposed onto what you have here. So this is what we call a split plot design. So the splitting can proceed as long as required. So you can have split plot, split plot, split plot, depending on how many levels of splitting is done. Now, randomization for the levels of the different factors are also done separately. So like we randomize the spraying and no spraying, and then we also randomize where the varieties will fall. So first random assign spraying to the main plot, and then the subplot you assign different variety. Now, the implication here is that when you're comparing spray and versus no spray, you're going to use a different error, a different experimental error. When you're looking at variety or a combination of variety and spraying, you're also going to use a different experimental error. So if you see, we are going to see the analysis of variance for split plot, and we see that it has different component, 2 different components. Somebody is asking maximum number of factors that can be included in the factorial experiment. Okay, remember when I was talking about the number of replication that one can have, the issue of blocking. So for you to determine the maximum number of factors you want to have in a factorial experiment will first of all depends on how many factors do you have, and what are your plans? Because one of the things that we do here is that remember, if you're going to have 2 factors, you're going to have what we call a 2-way interactions. If you're going to have 3 factors, you're going to have 3-way interactions. You're going to have 4 factors, you're going to have 4-way interaction. Now, as human beings, we are used to seeing things in 2 dimensions. Now, if you go to 3 dimensions, you're going to look at a box, you're going to start struggling. Now you're going to go for 4 dimensions, you're going to go for 5 dimensions. The more factors you have, the more complicated the interpretation your result is going to be. We are going to have maybe one of the sessions, maybe one training where we deal with factorial as for now, but we cannot tell the maximum number of factors you can have in a factorial experiment. It depends on your interest, but it also depends on the ease with which you're going to do the interpretation and other things. So this is how the split plot can be randomized in using the package Agricole. So the same thing that we've done is that you need to call that library first. Once you call the function, the package, the next thing that you need to do, you need to create your two factors. So factor 1, which is treatment 1, is the spray and no spray. And then treatment number 2 is the one for the variety. So remember here, we have this is our one set of treatment, and this is our second set of treatment. So this is what we call our treatment 1, and this is our treatment 2. So we create these two together, and then we go, this time now we go and pick design.split. So design.split means we are designing a split plot. We have a split plot design. And these are what you need in your function. You need to define the treatment that is going to be on the main plot, which in our case is going to be the spray or no spray. You need to define the treatment that's going to be on the subplot, which is our variety. You need to define the number of replication that you want to have. And then you need to define the design. Remember, we say split plot can be used with CRD, with RCBD, with Latin square. So here we're saying we are using it in RCBD, and then you need to define the series. The series where you have your 1, 1 or 1, 0, 2. So in this case, choose 2. If you change this to 1, then you'll have 1, 1. You have 1, 2, 1, 3. If you change it to, you change the 3 series to 3, then you'll have 1, 0, 0, 1, and then 1, 0, 0, 2. But this is merely a level of your plot or your experimental unit. Then we need to set the seed so that we're able to reproduce the same thing. We can set the kind. You need to read about the kind. I'm not going to talk about it here. So in most cases, what we always do is we can run a function in R with minimum changes. You use the default values. Okay, so here I define what treatment 1 is, what treatment 2, the number of replicate, and then the seeds. Okay, with this one here, you should be able to run your experimental design, to design your RCBD. Now, I want to use the next 30 minutes or so to say something little about incomplete block design, if you will allow me. So should we, I think we can still continue a little bit. Okay, good, thank you. Okay, the series, I can repeat a little bit about the series. So the first thing I said, don't worry about the series, okay? But it doesn't mean that I'm not going to talk about it. So the series can take value of 1. If you take a series of value of 1, then your numbering of the plots will start from 11. 11, 12, 13, and so on and so forth. If you go to you choose 2, let's just do it practically. I think that would be better. Okay. Just a little bit. So what we are going to do, we are just going to run the split, and then we are going to change a few things here and there, just to let me try to just do this for the sake of to explain the issue of the series. Okay, so what we need is we need to first create our treatment 1. We need to create our treatment 2. So here then we have our command. What we are going to do, we are going to run with the series we're going to run with series equal to 2, or let's start with run with series equal to 1. So we're going to run with series equal to 1, and then we'll see the results. So with the series equal to 1, you see now plot here, you have here your plot 1, 1, plot 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so so it's now talking about here. So you can see you have the block here. So here you have your block 1, 1, 1, 1, 1, 1, 1. You have your subplot 1, 2, 3, 4, 5, 6. So what is happening here is we are on the main plot 1, main plot 1, subplot 1, main plot 1, subplot 2, main plot 1, subplot 3, main plot 1, subplot 4, main plot 1, subplot 5, main plot 1, subplot 6. So you can see the 11 here. Then the next one is we move from 1 to 2, so you get 12. So subplot 2, main plot 2, subplot 1, main plot 2, subplot 2, and so on and so forth. Now, if we change this, so if we change the series now to 2, if we change the series to 2, we're going to see what will happen. Okay. Okay, so now you can see now we have moved from 1, 1 to 1, 0, 1. So what is literally happening is now that we have 2 places before we start numbering our plots. Okay. If we change to 3, then we'll have 3 places before we start numbering our plots. Okay, let me make 3. So you can see now you have 3 places before you start the number of the main plot comes in. So I think this should be able to handle the issue of series. Okay. So let me briefly talk about incomplete block design. And then I hand over to Ellen to continue with that. I'll probably take a few minutes. Okay. So we've looked at the importance of blocking, and that blocking, it decreases experimental error and provide more precise comparison of the treatment. So we're looking at what we call increased precision. So you'll be more precise in your your estimation. So increase in the precision. And this is one thing that we all want. We want an experiment with a little noise as possible. With blocking also will enable us to make comparison under more uniform conditions. So remember, you can have your comparison within the where there's uniform soil fertility. So let me go back a little bit and to re-emphasize this point. So we can make our comparison here where there's uniform condition, make our comparison here where there's uniform condition, and so on and so forth. Yeah, however, there are challenges that we face in blocking. So for example, a large number of treatment would require larger blocks. Like for example, say if you're doing plant breeding, if you have say maybe 250, you have 250 genotypes or lines that you want to test. Now, if you want to randomize complete block design, unless the size of your plot is just one line, it may be very difficult for you to get a block that would be enough to accommodate all those treatments. So the use of complete block may actually not be possible. So as the block gets larger, the condition becomes more heterogeneous, and then it actually decreases the precision now. There are also situations where natural grouping of experimental units will prohibit you from using blocking, from having a complete block. Let's say, for example, you want to use litters in pigs, for example, as your block. But then what you realize that if you have 10 treatments, you go and get somebody's sow that has only five piglets. So that means you cannot actually test all your 10 treatment in that litter. But that may be the only sets of litters that you have. So in a way, what will happen is then that we don't have to have a block that has equal size as the number of treatment that you have. We could have smaller blocks. Okay. So sometimes it's therefore necessary to block experimental unit into groups smaller than the complete replicates of all the treatment, like in RCBD or in a Latin square. And I give you an example here. I will show you an example in a minute. Okay, so we are still doing the blocking, but what happens is that our blocks is now smaller than the number of treatment that we have. So if, for example, let's say, for example, we have here so let's say, for example, here we have a block here, block of size 6. Okay. Now, if we have like 10 treatments, you see our block can only take 6 of them. So for us to call a block complete, a block should be able to have 10 experimental units so that you have all your 10 treatments. So in this case now, the block can only take 6. Therefore, our block become what we call incomplete. Instead of having a complete block, we have incomplete block. Okay. So incomplete block can be classified into 2 major groups. The first one is we can look at randomization using one blocking factor. So we have randomized incomplete block design. So from RCBD, we can get randomized incomplete block design. And then from a Latin square, we can also get incomplete block design. So you can get incomplete block design when you're using one blocking factor or when you're using 2 blocking factor. The other way of categorizing or classifying incomplete block design will depend on whether the design is balanced, in which case if we have treatment A and B, let's say we have treatment A, B, and C. Now, we should compare A versus B, A versus C. These are the possible comparison that we can make. Okay. So each pair of treatment should occur equal number of time in the same block. Okay, and so this is what we call a balanced incomplete block design. So with balanced incomplete block design, that means if I have 3 treatments, each of the 3 pairs that I have should occur equal number of times in the same block. The design may also be what we call partially balanced. So with partially balanced, that means not all pairs will occur equal number of times. So some pairs may occur once, others may occur together twice, others may not occur together may not occur together all throughout your experiment. So the classification of incomplete block design can be looked at in terms of how many blocking factors you're dealing with. You can have randomized incomplete block design if you're dealing with 1 factor only, or you can have incomplete Latin square design if you're dealing with 2 factors. So the incomplete Latin squares are what we call row column designs. So there are a number of row column designs that are very, very famous in agriculture and other fields. So for balanced incomplete block design, all treatments are replicated equal number of times. So you have your A, B, and C. So if A is replicated 3 times, B should also be replicated 3 times, and then C should also be replicated 3 times. Otherwise, it will become imbalanced or unbalanced. Each pair of treatment occur in the same block equal number of times. So if A and B occur 2 times together in a block, B and C should also occur the same number of times. The implication is that when you're making comparison, then they're all going to be compared with the same precision, and because they have equal number of replications. So that is what we have as balanced incomplete block design. So the limitation can be there, but literally you can balance any number of treatment and any block size. The only thing is that treatment and block size determine the number of replication required for balance. If you have very many treatments and you have smaller blocks, that means you're going to have several replication to allow all pairs of treatment to occur equal number of times. So this actually always complicates the use of balanced incomplete block design, especially in field experimentation or even in industries. So you say, can you apply replication in management and economics, and you want examples? The question is, can you do an experiment in economics? If yes, okay. So, I mean, what kind of experiment can you do in economics that would be? So let's say, for example, well, I don't, there are experiments that people have, for example, let's say you want to see how people park their cars in a parking lot. Do people park where there are other cars, or people park, they can park independently? So what you could do, you could get a parking lot, okay, and you park your car there. Get another parking lot, park another car there, get another parking lot, and park your car there. So then you can literally set your video and wait to see. Maybe somebody drives in and you see where they will park. Will they park here? Will they park there? Will they park there? Will they park there? Will they park here, here, here? So if you think so, this can actually be your replicate number 1. This can be your replicate number 2. That can be your replicate number 3. So the question is, can you design an experiment in economics? If the answer is yes, you need to define what's your experimental unit, what's your treatment, and can the experimental unit be repeated? Okay. I hope that answered the questions that has been raised. So what we're saying here that often the minimum number of replication required for balance is too large to be practical. Okay, so this is a simple experiment. A simple experiment for balancing complete block design. This is in one of the statistical or experimental design book. So what these people were trying to study, they are trying to study the effect of temperature inhibition on seed germination. So the treatment in this case, they would subject the seeds to 25 degrees centigrade, 30 degrees centigrade, 35 degrees centigrade, and 40 degrees centigrade. Okay, so you can get yourself maybe an incubator, put the seed inside there and set that temperature, and then you wait what will happen. So you have a control environmental chamber. So now here, a single chamber constitutes an experimental unit. Okay, and each run of the experiment constitutes a block. So our experimental unit is a chamber, a control, a growth chamber. Okay, one complete block. We have four treatments here. So what would be the size of the block if we had to use randomized complete block design? I need some answers in the chat. For a complete block design, how many experimental units do we need within a block? Within a block? Four. Okay. Okay. So we need four. Good. So we need four within so what happens here is that you're going to run this thing in a lab. So a technician will come and set one experiment at a go. And that would be what we call a block. So what you have here then is you would require four chambers. But in this case, what is happening is that only 3 chambers were available. So that means in one run, you can only run 3 instead of 4. So therefore, our block now becomes incomplete because instead of having all the 4 treatment, we can only take 3 treatment at a time. Okay. So this is what the thing is. That so in the first run, so a technician comes and sets up. This is our chamber number 1, number 2, number 3. So number 1, it was we randomized 25 degrees in it. Number 2 was 30 degrees, and number 4 was 40 degrees. So this one was run. So let's say it runs for a week. The seed germinates. You get the thing off. You get a second run. You get a third run. And then you get your 4th run. So in this case, although the number of treatments are few, there is a limitation in the number of chambers that we have in the lab. So in a way, therefore, that actually restricts the number of treatment that we can use. Okay. So now we need to see, is this a balanced incomplete block design? If it is a balanced incomplete block design, we are saying the number of times each pair of comparison, each pair of treatment appear together should be equal. So let's look at 25 and 30. So there in the first run, we have 25 and 30. In the second run, we have 25 and 30. In the third run, there's no 25 and 30. And in the 4th run, there's also no that, okay? So 25 and 30 appears together in 2 blocks. That is in round 1 and round 2. Let's look at 30 and 40. So 30 and 40 appears together here. Once, that and 40 appears together here twice. Okay. So now let us look at 40 and 25. I need a new color. Okay, let me take a black color. So 40 and 25, they are here. Once, 40 and 25, they are here twice. Okay, so what we can see from here is that all pairwise, okay, all the pairs are occurring together 2 times. Okay, so that will be our randomized complete block design. That will be our balancing complete block design. Question? Choice of experiment. How do you choose an experiment? Okay, good. Yesterday, I had a brief introduction to research process, and we talked about the importance of hypothesis testing and how hypothesis testing can help you to design a good study, but that also stems from the problem that you're trying to study. So you need to identify the problem that is under study, whether it is low yield or what, and after you've identified the problem, you need to look at the hypothesis. So the hypothesis and the objective of the study will guide you in the choice of your treatments and your design and the design of your treatment. Okay. So there's just a simple formula that you can use to determine the total number of so let T be the number of treatments. So in our case, we had 4 treatments. Let B be the number of blocks. In our case, we have 4 blocks. And then let K be the size of the block. So the size of the block is simply the number of experimental units that are there in that block. In our case, the size of the block should be less than the number of treatment because we don't have a complete block. So in our case, our K is equal to 3, which is less than 4. That is the number of treatment that we are dealing with. So to get the total number of experimental unit that is required, you need to know how many treatments you have and how many times you want to replicate. And then that should also be able to equal to the block size times the number of blocks that you'll have. So in our case here, we need 12 different experimental units. And so that's why we had to run 4 times to get our 12 experimental units that you have. I know formulas can make some of you go to sleep or scared, but please, this one is just, I put this one just to decorate my slides, but it cannot stop you from having a look at it. Okay, so here, yes, a social scientist can use randomized complete block design as long as you know what you're blocking against. Okay, you can block like the example I tried to describe. You can block by location. Let's say you do your experiment of you do your car parking experiment. You do it in different cities. The cities can be used as a block. But then you should be able to get a number of parking lots within the city that can make you test all your treatments. Okay, I'm not going to talk about this for now. I'm going to show you how we can use Agricole again to design a balanced incomplete block design. So this time we are going to use design.bib. So BIB is balanced incomplete block design. Now, TRT is your treatment. K is the size of your block. Now, in this case, R, you can leave R as null. Then the program will tell you how many replicates you need depending on the 2 numbers here, depending on the number of treatment and then the size of the block based on this formula here. So you don't need to specify the number of replication. You need to tell the number of treatment and K, then it will tell you how many replication you actually require. So once you do this, you can run and then you have that done. So this is for our treatment here. For example, we have our this is our treatment. We put it here. Then K, we are saying in each block, we are going to only run 3. We will only run 3. We only have 3 runs in each block. And then we don't fill in the number of replication. It will do it for us. You include the series. You have the seed if you want to repeat. We still using super duper. You can select a few others, a maximum number of repetitions, and so on and so forth. Okay. Now this number of repetition is important because you don't want to. I mean, you may say at most I can afford 20 replicates. So if it is not possible, then I need to go for partially balancing complete block design. So with this, you run, and then this is our assigning. So here you get our first block here, the first 3. So you have 40, 35, and 30. The next 3, you have 25, 30, and 35. The next 3, you'll have your 40, 35, 25, and then the next 3. So you can see 40 and 35 is here once, 40 and 35 is here twice. So if you go and look at 35 and 30 is here once, 35, 30 is there. 25 and 30 is there, and then up. So you can actually design that, okay? What we are doing with you now is we are trying to give you actually a head start. So you are good to go after this, okay? And then the other thing that I'm going to talk about, I'm just going to define this. I'm not going to say anything more about this. So partially balancing complete block design would mean that the number of treatment, the combination that we talked about, like here we're saying this and this occur twice, this and every pair here occur twice. With balancing complete block design, you can say, like, for example, can have 40 and 30 occurring together, let's say once, okay? Then 40 and 25 occurring together, say 2 times. Maybe 40 and 35 occurring together 0 times, okay? And then you have all the, so that's what called partially balanced incomplete block design, okay? You can also generate that if that is what you require. I'm not going to look into this example. You have the material, so you will actually have it. In BIB, what happens if the 4th treatment is abandoned? No, it's not abandoned. I mean, it's only that the 4th treatment is not abandoned. What we're saying is that we need now to arrange our block in such a way that at least we can make each pair to occur with the other one. So you can see from here that our 4th treatment is the 40, but we are not abandoning it. What we are doing is that we can, put 3, 3, but ensure that every time we have the pairs, as the pairs are this pair, for example, we ensure that they occur together twice, or depending on how your design is. So it's not abandoned, it's still within there. Okay, so I'm going to talk briefly about the row column design. And then I would put a little bit of time on the alpha lattice design, because that's what mostly used by plant breeders. It's just a brief, this is just a brief introduction. So we've seen that a Latin square is a complete block design to control variation in 2 directions. You can control using the rows as a blocking factor. You can control using column as a blocking factor. So, but we looked at a situation where sometimes this becomes impractical because of the large number of experimental units that is required. So if you have 10 treatments, that you need 100 experimental units. If you have 20 treatments, you need 400 experimental units. So what happened is then that we can decide to go for what we call row column design, where either the rows or the columns or both are incomplete. So remember in our Latin square, let me go back to Latin square. Yeah, so this is a Latin square. So remember here, our row, this row here, we have 4 rows. We also have 4 columns. So we can have a situation where we can decide to get rid of this. Okay. So now instead of having a 4 by 4, okay, we now have a 3 by 4, 3 rows and 4 columns. So now this becomes now incomplete. It's an incomplete Latin square design. You can also have you can't have this one here. Okay, so we can also cut off the 4th machine. So in this case, then we have a 4 by 3 by 3. Or you can cut off both of them like this. So you end up with a 3 by 3, you're still in a Latin square, but now in this case is not complete. Okay, so that's what the statement that we talked about implies. That the CRD is not running, but are they running the script? Okay, maybe we can handle that one later. Okay, so what we're saying here is that you can have either row or column or both as incomplete blocks, which I already showed you. We have what called the Youden squares, where 2 or more rows are omitted from a Latin square. This is also famous design of the experiment that was used to be used a lot. Now, the problem with these designs were that it used to be very difficult to generate this design because they used to do a lot of this lottery method. But with at the back of some statistical book, you'd actually have a series of design that are already, the randomization has already been done for you. You just pick one of them and use. Yeah, but these days we saw how R can help us to actually design. Let me just show you an example of a row column design and the application, where it can come. So this one here is based on, this was on cars. You know, most of the normal small cars that we have four wheels. So if you're testing tires, you can test if you're having a treatment that involves the tires, each car can only have 4 wheels. So if you have more than 4 treatments, that means each car is not going to have it's going to be complete. So here we have an experiment where we have 7 cars, and we have, of course, each car has only 4 wheels. So, but there are 7 treatments. So what we have here now, if you look at the row, the row is complete. The row has all the 7 treatments. So it's a randomized complete block design. Why? Because all the cars have position as tire number 1. Okay. The row 2 is also complete. Row 3 is also complete. because there are 7 treatments. So there are 7 cars. So each car has wheel number 1, number 2, number 3, number 4. Now, but when we come to the cars themselves, each car only has 4 tires. So car number 1 cannot take all the 7 treatments, can only take 4 of the treatment. So here you have your 3, 5, 6, and 7. So 1, 2, 1, 2, and 4 are not here. Then here you have another sets of treatment. Here you have another sets of treatment. Here you have another sets of treatment. And then there you have another sets of treatment. So this is a row column designed with 7 treatment, evaluated on 4 car tire positions, which is the 4 rows and the 7 columns which constitute the cars. Okay. And then I talked briefly about the Jordan squares. So these are incomplete Latin square with 2 or more rows from the Latin squares omitted. That is all that we can say at the moment. If you want, you can read more about Jordan squares. Okay. So here, okay, this is a good example that could probably go for a Latin square. So somebody said, treat 1 case in food science where you treat 6 seed varieties to soaking for 12 hours, 30 hours, 48 hours. Then you boil a portion of each soak set for 30 minutes, 45 minutes, 60 minutes. Can this fit into a block? Okay, so the first thing here is that what are the treatments? Here we have variety as a factor. And how many varieties are there? No, this one. No, somebody posted this, then the thing went away. Let me pull it up. Okay. So here you have varieties, and they say there are 6 varieties. And then you have soaking time, and there are 3 soaking time. And then here you have cooking time. So here there are 3 cooking times. So this can be a typical factorial experiment, but in this case you have 6 factors. You have 3, not 6 factors. You have 3 factors. So it's going to be a 6 by 3 by 3 factorial. Now the 6 by 3 by 3 factorial now is we are going to have a set of combination. Now the issue now is when we go to the design, the question then is there one of these treatment here that require a wider application? Because if, for example, you are doing the soaking of the seeds, of course you cannot one thing is, for example, let's say you have your seeds in small packets that you can put them in water for 12 hours. So you could actually decide that, say, well, we can use a split plot in this particular case. And then the main plot factor, we could put soaking. And then you then look at there is also, so there is the soaking and boiling, I think. Well, I'm going to give this as an exercise. Okay. So I'm going to copy this and put it in a chart again. So what you need is you need to copy this. First copy this somewhere, and then what we are going to do is here we are going to try to treat this. So what we're going to do, we're going to look at, please, first don't post anything. I'm going to talk about the number of replication and other things. So what we are going to do here is, this is a factorial experiment with 3 factors. One is at level 6, the other one is at level 12, and 3, and then the other one is also at level 3. So it is going to be 6 by 3 by 3. Now, this can, if it is in the lab, for example, we can use completely randomized design. We can also use a randomized complete block design. We can also use a split plot design. So I would want you to look at a scenario where you're going to use 1, CRD, 2, RCBD, and 3, you're going to use a split plot. Now, we are going to go for 2 replications. Okay, we are going to write it in the Word document, and then we will share. So you're going to have two replications, and then you're going to look at you're going to design for me a study, and you're going to generate for me a book, a field book that we are going to use for this particular experiment. So thank you for bringing this out, and we're going to use it. So let me just first paste it onto. Okay. So now let's. I'm just going to say something briefly about resolvable and cyclic incomplete block design. These designs were very famous one time in United Kingdoms. The reason why they were very famous in United Kingdoms by then was that the number for any experiment that you would carry out, the number of replications were dictated by law. So you said if you're doing wheat experiments, you need to have this number of replication. So that means the issue of using balanced incomplete block design or partially balanced incomplete block design was out of the question, because you need the number, you need the replication. So what this resolvable incomplete block design does would be, they were interested in grouping treatment into replication. But in this case, the blocks are smaller. So that means you can have 10 blocks to actually accommodate all your treatment, which is one set of replicate. So these designs were mainly, they mainly brought them out to help solve the problem of having replication. The advantage of having a complete replication as a group was that you can apply treatments. You can actually do field operations or management replicate by replicate. So resolvable designs where blocks are grouped so that each group or block constitute one complete replication of treatment. So what would happen would be, if I have 10 treatments, let's say I have 10 treatments, and I have my block. Let's say I have my block of size K equals to 5. Okay, so for me to have all my 10 treatment together, I need 2 blocks. I need the first block that will take 5, and then the second block that will take the other 5. So here, this one here will constitute my full replicate. My full replicate is a set of 10 treatment, but I can divide the 10 treatment into 2 blocks, each of size 5. So that was the whole idea. The whole idea was that if I can group my block in such a way that a certain group of block can give me the number of replication, can give me a complete replicate, then I have a good design. So as I indicated, it was actually useful for trial management in that you can then do everything replicate by replicate basis. So things like planting, things like weeding, things like data collection could actually be done on the basis of replicate. And also it was noted that you can actually lose a complete replicate without actually affecting the experiment, because if I lose this one set, I can still get another set from somewhere. Okay, so if you have 2 or more complete replication, you can actually analyze them as randomized complete block design in case it turns out that the blocking is not effective. So the resolvable designs are designed where you can group your blocks in such a way that each group of block will constitute one complete replicate. So that means I have one group, 2 blocks here will give me a complete replicate. I have another 2 blocks here that will give me another replicate. I have another 2 blocks here that will give me another replicate. Okay. So the challenge here is then that you need to arrange your blocks in such a way that the only issue here is now is the notation. So K is the size of the block, R is the number of replication, T is the number of treatment, and S is the number of blocks that will constitute a full replicate. So if I go back here, how many blocks do we need to have a complete replicate? We need 2 blocks. So our S in this case is equal to 2. Our K is equal to how many experimental units are there within this. So our K in this case is equal to 5. And then our number of replicates here. So we have one group here, another group there, another group here. So our number of replicate R is equal to 3. That is what we have. So we have S, we have K, we have R, and then we have T, which is the number of treatment. So our T is equal to 10. So there are relationships that we need to maintain between S, K, R, and T. And this one will dictate on how many treatment you need if you specify a number of replication that you have. Okay. So the total number of blocks should satisfy the relationship R times S should be greater or equal to T plus R minus 1. So this is kind of a mathematical relationship that you don't need to bother yourself with at the moment. But what we need to know is that the number of treatment should be related to the number of blocks that you need to have a complete set, and then the number, the size of the block. So if you have 10 treatments, it should fit into. So if I have K, if K is equal to 2, then the only value that S will take should be 5, so that the 2 sides are equal. And that means it is always important to have a certain number of treatment. If you don't have a certain number of treatment, you may need to add some checks in order to actually come with the values that you actually look at. So this relationship is very, very important. The total number of treatment is a multiple of the number of units per block. Total number of treatment is a multiple of the number of units per block. When this design came up, the issue that was also now at that time was how do we do the randomization process? So from the resolvable, we came up with what called the cyclic design. So the cyclic designs are row column design that are easy to construct. So the whole advantage of this is that they are very easy to construct. You just construct them using some very simple method that I'm not going to show for you now. And one of the most beautiful of all this design is what we call the alpha design. And this is going to be the second last slide that I'm going to talk about. I know you're all tired now. It has been a very long day, a long morning for you. Okay, so let me just talk about this and then I show you how you can generate it, and then we can talk about other things later. Okay, so alpha designs are first of all resolvable design. They were developed in the 70s by Peterson and William. Okay, I told you already that the number of varieties and the number of replication were fixed by statutory requirements. So you can only have a fixed number that you have. So because the varieties the number of varieties were very many, so therefore it will necessitate the use of income. And then the issue of field management was also critical in that you need to group your experimental units somehow into replication, complete sets of replication. So the existing resolvable design by then will not accommodate all the number of varieties and block required by the trial. So these guys came out with a new design, and this design has no limitation on the size of the block. So you can use it for any size of the block. The only thing is now that this relationship between T and SK should be maintained. So if this relationship is not maintained, then you will not use this design. So if I have 100 treatments, then somehow these 100 treatments should be related to S and K. So if I have a certain number of, if my block is equal to 10, that means I need S should also be equal to 10, so that you remember that 99 is not very easy to get 99 unless you get a 33 by something that you'd actually have here. So you may need to add 1 or 2 varieties to make 100, then you can use a 10 by 10 alpha lattice design. So these are very efficient design. It exists in some combination. So this is a simple way of how to generate the design. So the first thing that we have is we need to still have our treatment. So in this case, we have 100 treatments. So I just treat as 1 to 100. And then I just try to do some small manipulation here. So T is just simply the length of the length of treatment. This one equal to 5. So our block, the size of our block is equal to 5. That means each block that we have can only take 5 observations, 5 of our 10 treatments. So that means how many blocks I need to take the 100 would be, I need my 100 divided by 5 So I need 20 blocks in order to have a complete set. So sometimes you have this is called maybe 20 by 5 alpha lattice. Okay, so once you define this, then we go back to our design function here. And we say design.alpha this time for alpha lattice. We need to define our treatment. We need to define our K. You need to define your R. And then you need to set up this. And with that, you should be able to design, to come up with a design that you have. So I think for now, I can answer a few questions, and then I'll come back to some of this again as we come back for in other days, maybe tomorrow or the next day once I come back again, or any of my colleagues will actually handle it. I know it has been toward the end, it has been a little bit hectic, so maybe we would have a bit of a break before we go in for the second part of the day. They say the difficulty is that the difficulty comes from the fact that most experimental designs were born out of culture, and so a wide range of examples. So what is the best? The best is to understand its explanation and transfer. Yeah, well, that is true. So what we remember what I started with yesterday, and I said, it doesn't matter which field you are in, the principles of experimental design remains the same. So you need to do replication, you need to do randomization, you need to do blocking if it is necessary. Okay, so what does the seed represent? I think I talked about that already. I said the seeds is simply used for you to specify that particular one randomization set that you will get. If you change the seed, you get a different number. How is K determined? K is the size of the block. And remember, you want a block that is uniform. So the uniformity of the experimental material will determine the size of the block. So if, for example, you're looking for people to human being, you want to do experiment on human beings, then what you certainly need would be to select. You can go and select. So if, for example, you're looking for people with big heads, or I mean, you're grouping human beings based on the size of their head. Now, it may be difficult to get people with very big heads, so that can determine, then can actually restrict the sample. It can restrict for you the size of the block. If you can only get 10 people with big heads, then the size of your block is probably going to be restricted to 10. If you can get 15, then you can go up to 15. So will you also touch non-experimental studies? Yes, the next after this, we are going to talk about sampling surveys, but everything else that we are talking about that applies in experimental design will also apply in other like in sampling survey. Big head. Okay, so can we have a break? How many minutes? Let's have 10 minutes. Okay, let's have 10 minutes.
Hello, everyone. Can you hear me? Please type in the chat if you can hear me. Okay, let's get started with the next session. It's going to last for 1 hour and some few minutes. Then maybe if we get at 2 and we are not yet done, we can start from there tomorrow morning. Okay, so what I'm going to be covering is an overview of sampling surveys. Dr. Thomas has discussed about experimental designs and what are the different approaches that you can use during the analysis of experiments. So now we are going to look at the other side of the coin, what happens in case of surveys. So it's what we are going to look at now. But I would still encourage you that we discussed the different concepts, try to see how can you really take this information on your own study or on the data that you're working on right now. So with the overview of sampling surveys, I'm going to first talk about introduction to sampling methods, but we need to first understand a second. We need to understand what a survey is. So most of the time, when you're looking at a population survey, what is important is that we need to draw an inference by the end of the day from a population. And because a population is very big, okay, because the population is very big and I mean, we need a lot of cost. So most of the time what happens is that we take a subset of the population, and this is what we refer to as a sample. So what we do, we draw a sample, and then we use our sample to make an inference of what is happening in the entire population. So you can draw inferences or conclusions about the characteristics of the population. It could be in terms of income. You can look at the behavior or the different opinions depending on the population group that you're looking at. Okay, but most of the time when we're looking at sample surveys, it is always good that a good survey aims to select samples in whereby the characteristics of a sample are similar to that of the population. So in this particular case, you'll be avoiding the bias in the selection. So we are trying to see that has the sample that has been picked, does it represent the underlying population? So as we move out to do our surveys, all these factors have to be put into consideration, because by the end of the day, what we need to avoid is the bias selection. So, and usually this happens in a random process. So, I mean, there is no, like you don't have any specific treatment that you're going to do. Most of the time, this is done using a random process. So, but remember, there is no sample survey that is perfect. So most of the things, yes, you might want to pick a sample that is a representative of the population. We want to avoid bias, but most of the time there are they've talked about noise. Okay, when Thomas was explaining about the noise yesterday that happened during when you're performing an experiment, it's the same thing even in surveys. You cannot avoid errors, so errors are unavoidable. So in this case, sometimes we can refer to an error that can happen in a sample as a sampling error, or the other term that you can use is the margin of error, because most of the time is that not all the elements within the population are selected. So it is possible that the sample that you've selected maybe might not match with the population that you want. So that's discrepancy that exists between the estimated and then the true population value is what we refer to as a sampling error, or you can call it the margin of error. And it happens in all, when you're doing surveys or experiments, you cannot avoid errors. Though the main point is that we need to ensure that our error is as small as possible, because we want to check that in case the margin of error is very small, then that drives us to the fact that we are attending to the true population value. When it is wide, then that is a different case. We're trying to see how can we reduce our error to be as small as possible. Okay. So during surveys, yes, the aim is to see that we minimize the sampling errors, but also we need to look at, all this will depend in terms of the different resources that we need. So with the population surveys, we need to consider a design that gives us a low sampling error. But when you read in most of the literature or certain published work, one of the accepted, most of the cutoff point for the accepted error, it lies between a plus or minus 5%, all right? So that is 0.05. We can take an example. When you look at this particular example that I'm showing, that an opinion poll on Uganda's health concern was conducted by Gallup organization between October 3rd, that was May 1997. And the survey reported that 29% adults consider AIDS is the most urgent health problem of Uganda, is supposed to, with a marginal error of a plus or minus 3%. The result was based on telephone interview of 872 adults. Let me first stop share this and I share again. I think I want to confirm that I'm sharing the right PowerPoint. Just a second. Okay. Just give me a second. I'm confirming the data point I've shared. Okay. I think I'm set to go now. All right, let's continue. So we are looking at, yes, now with this particular example that we are considering, the 29% is our population estimate, and the population that was considering, they were adults. So when you look at this, the plus or minus 3%, that is the margin of error. And then what was the method of administration of the survey? These were telephone interviews, and our sample size, it was 872. So this is, so the point is about the margin of error or the sampling error that you expect by the end of the day. We say that it has to be as small as possible. In this particular survey that was done for them, they took it as a plus or minus 3%. But most of the time when you look in published literature, the cutoff point is plus or minus 5%. And how does this one come about? It still goes back on the objective of the study that you are setting. Okay, all right. So because most of the time, sometimes it is hard to really have a true estimate. So that's why we put, to have that confidence, we put a plus or minus our margin error. So basing on this particular example that I've just showed out, we see that it has got two binary outcomes, whereby 29% of the interviews of the people that responded said yes, that it was an urgent healthy problem. So if you get 29%, it implies that 71% are the ones that the ones responded that no, it wasn't an urgent healthy problem. So if you look at the 29% of the respondents that who said yes, then it implies that that is our probability of success. Okay, you can call it P, and then the 71%, which is 1 minus P, those individuals that responded to no. So for us to get the total number of respondents, all right, that responded yes, then it implies that, because if you see here, we know the total group, which is 872. Okay, that is our sample size. So for us to get to know the number of respondents that said yes, it was an urgent healthy problem, then it implies that we get the 0.29, that is those who responded yes, we multiply by the total number of the sample size. So in total, for those who said yes, there were 253, and then those who said no, it was, we get those who said no, that is at 0.71. We multiply by the total number, we come up with 619. So anyway, the point is that is what is the chance that people responded to the interview, said that it was an urgent health problem. So it is this is how they obtained the 0.29, getting the total of those who said yes divided by the overall total. Okay, however, yes, we saw that 29% where they agreed with a health concern, but how much, how we need to understand the level of confidence. And we're looking at best statistics, most of the time we use the 95% confidence interval or the confidence limit, whereby we want to understand, we want to check and see, well, 29%, is it really our true estimate or our true parameter value? So in case it's the case, but to what level, what limit, what margin of error can we really conclude in at a certain confidence interval? So we all know, I don't know whether we are all familiar with confidence intervals. The formula for confidence interval is, it is the one that I'm showing here, where I'm moving the mouse. Here I've got my P, that is the estimate, the 29%, the point estimate, which has given us 29%. And then this is a z-value that can be obtained from the statistical tables. This z-value, it is at 95% confidence interval. And then the standard error for our point estimate. All these are just mathematical terms, that expression that you can remember. You don't need to cram them because they're all over in textbooks, they're all over on internet. So it's a matter of understanding how they work, and then that will be perfect. So when you check the Z value for the 95% confidence interval, it is always 1.96 and it will never change. And then our formula for the standard error of our estimate, it's given as P, the square, it's usually the given as PQ over N, or sometimes it is written as S over root N, depending on the sample that you are considering. But looking at what we are having, our P, which is the respondents that said yes, is 0.29, and then the Q, that is 1 minus P. Q is equal to 1 minus P. So this is 1.71. We know the total number is 872. Okay, so when you do the calculations, the whole of this expression, we are coming up with 0.03. And it's what we had, if you go back, it's what we had here, which was the 3%, how it was calculated. So it implies that we had our estimate as 0.29. And this portion here, this part here from the plus or minus, the whole of this particular side, this is what we call the margin of error. And in our case, it is 0.03. So it implies that we can be 95% confident, confident that our true range that was determined as 95% lies between 0.26 to 0.32, implying that if this is my estimate, you add a 0.03, okay? And then, so that will give you 0.32, and then the lower limits, okay? So the confidence interval, it's a limit that we can be confident where we can lie and agree that, well, we can be, we agree that the respondent of that AIDS with an healthy problem is 29% within this confidence limit or confidence interval, because remember, like we said, that when you're carrying out these surveys, you expect that it's not going to be a perfect survey that you're going to get. Sometimes there is an expected noise or error that you expect to get at the end of the day. Though, remember, the aim is to make it as small as possible. How can you perform a survey to ensure that your error is as small as possible? So in this particular case, in this survey that was conducted, we are having 0.03. And the 0.03 is what we call a margin of error. Some people can call it a sampling error, or the noise that was got. Okay, let me stop in the for a while, and I ask in the chat if we're on the same page. Type yes if we're on the same page. Okay. Okay, that's great. Let's continue. So, as I was mentioning, so we are having our P, the point estimate, then plus or minus, this is our Z value at 0.05. That is at 95% confidence interval. It is just a mathematical expression, like I mentioned earlier. It could be found you can get it from internet, from the different mathematical textbooks or even statistical textbooks. So in general, maybe to generalize, to move it from the math bit. So we have an estimate plus or minus the margin of error, or the error, the sampling error. All those terms mean the same thing. So our estimate was 29%, and then plus or minus 3%. So whatever term or expression that is above, that is after the plus or minus, is what we call the margin of error. If I'm to take you back briefly, the whole of this expression from 1.96 and the square root of this is what we refer to as the margin of error. Okay, so now we know what a margin of error is. All we calculated that it was 0.03. But it's quite interesting is that from this particular expression, if you look at it critically, we can be able to because from here we know that we know our n, that it's 872, but in case the n is not given, then it implies that from this particular expression, I can be able to calculate my sample size. Okay, so assuming that I make my n, which is 872, the subject. So this is just I cross multiply, and then my margin of error comes down here. So if this is 872 is my n, that is my sample size. This is my z at 95% confidence interval. But in this particular case, to remove a square root, we squared both sides, and then we've got the PQ over D. Remember what our P is, that is the number of that responded, it was a health concern, and then the ones that responded, the Q, that is the no. Then now my D squared, it's what I'm referring to as the margin of error. So when you look at this particular expression, we are having our N, and this method can be generalized depending on the objective of the study that you can do. So if you know or you can guess the estimated value, that is the P, then it implies that you can be able to calculate the sample size with a specified margin of error or the sampling error. So, however, we need to understand that most of the time it helps us to determine whether you need a large sample or a small sample size. So now, like from the previous questions or from what the example that I've just showed, what the various questions that should come at the back of your mind from that poll, maybe you can ask that what was the target population, all right? So what was the sample population? We saw that these were the adults that were reached using a telephone. So how was the survey conducted, the method? So if it was a telephone interview, how was the sample selected? Then how reliable are the estimates? How much confidence do you have on the estimates, etc., etc. So all these questions that you're trying to explore can be answered during, all these questions can be answered from the role of sample size can answer all those questions. So as we continue, we said already what a survey is, okay? So we conducted to measure different characteristics within the population, and the process of carrying out a survey whereby we are getting a subpopulation from the entire population or from the big population, that is what we refer to as sampling. But by the end of the day, when we get this sample space, all it's supposed us is to draw conclusion that this conclusion, or call them inferences, about the entire population. So that is when you have a survey design and then a sampling strategy, we end up with the survey sampling. So, well, depending on the objective of your study and the research, it calls for different survey design and then a different sampling procedure. But I mean, you need to understand what survey design is appropriate for your study and how are you going to conduct the survey. It is important. And then also at the back of your mind, you need to ask yourself during the sampling procedure, what sample size is needed for my study. Okay, so we are going to look at some of the types of the survey designs that can be used during sampling. Number one, we have what we call the cross-sectional surveys. And practically speaking, these are most of the time, especially when it comes, for example, to student thesis, or they usually conduct cross-section surveys. And this is just data that is collected at time point. For example, maybe you want to understand the students' perception towards use of internet. Then you go out, it's a university setting, you get the students, you design your questionnaire, and then they give you their results. After maybe collecting data, you do the analysis, and I mean, the data collection procedure has ended, stopped. So that is, you collect data at a particular point in time. So that is those cross-sectional surveys, okay? You do it at a one point in time, and you end that. Whereas with the longitudinal surveys, these ones are different. Most of the time when it comes to longitudinal surveys, the surveys, for example, you can look at it in terms of trends, whereby the sample of the population at different time points. For example, you can take a certain group of patients, okay? Maybe they come to hospitals at various intervals, and then you're checking their, it could be, well, you're working on them on a particular disease, and they have to come back maybe after 3 months or after 4 months. So you keep tracking this one unit at up to a certain point. So in case you're tracking this particular person, the unit in a sample, for example, maybe for more than once, then we refer to that as longitudinal surveys. So in this particular case, it could be in terms of the trends, all right? And then it could be a cohort. In this case, for example, you can say you're tracking for the students that have reported at university, For example, the first years, the moment they report at the university, then you track the performance, then you continue when they're in the second year, then you continue when they're in the third year. So that is a cohort kind of study. Okay, you study the study of a same population each time over a period. And then when it comes to, for a case of the panel, this is just a study of a sample of respondents at various time points. But the point is, when it comes to longitudinal surveys, you study a particular population for different time points. You don't just study them at one point and then you stop there. So of course there are pros and cons about both the cross-section surveys and then longitudinal surveys, but it all depends on the kind of survey design that you put specifically to your research. So now we are moving on to what we call the sampling procedure. So when you're conducting your surveys, of course, there are various procedures that you can use. We have what we call the non-probability sampling and then the probability sampling procedures. With the non-probability sampling procedures, of course, they also have got their types like conveniency, purposive, then the snowball. And then when you come to probability sampling procedures, we have simple random sampling, systematic, stratified, cluster. And by the end of the day, when you look at probability sampling procedures, all these ones, at the end of the day, they all merge into what we call a multiple sampling procedure. They're all compositions within a mount stage. But we are going to go into details of all what each means and where it can be applied. Okay, now with the types of samples, we say that we've got probability samples. We are going to go into them in details, and then we've also talked about the non-probability samples. But still, most of the time, all the things have got advantages and disadvantages. There are some people that you'll find who will tell you, I'm going to go in for non-probability sampling procedures. And then somebody else will go in for probability sampling procedures. But we need to understand to weigh the pros and the cons. What are the advantages and what are the disadvantages? Though when it comes to scientific writing, most of the time we recommend the use of probability sampling procedures. So what could be the advantages? So in this particular case, when you're using probability sampling approaches, they provide you with the data that you collected is supposed to provide you with a known quality, and then also you can easily control the sample that you're going to use over other non-sampling procedures or non-sampling source of errors. And at the same time, the probability can easily be analyzed and then interpreted into your data, especially now that we know well already for example, we talked about the margin of error, whereby its cutoff point is ±5. So you can easily interpret, even if you have such a kind of results within your analysis, and then be able to communicate to a layman person or to an audience that is really not so much in statistics. So that is the advantage with the probability sample. Yet when it comes to non-probability sampling, these ones are purposely selected without any confidence, because by the end of the day, most of the time, like we're going to look at the various examples within non-probability sampling, like convenient sampling. It is at your convenience, so you start somewhere and you start conducting your survey of what you want. So most of the time, you can do them without purposely selected without any confidence, and you can do the selection within the survey that is likely to be biased. Yet what we want to see that in our sampling, we see that there is no bias. And in this particular case, there is no mathematical property. And most all the non-probability sampling approaches do not take the scientific part in mind. So by the end of the day, yes, by the end of the day, it might be hard for us to have a really scientific conclusion when it comes to non-probability sampling. All right, so let's move on. What are the characteristics of a good survey sampling? okay? Because when you're going out there to the field, it's always important to understand, yes, you're going to carry out a survey, but what are the different characteristics of a good survey? So of course, there are very many, but most of the time, you have to look at the issue of time. Are you able to use the survey? Is it in a reasonable and a timely manner? You have to look at the issue of cost consideration. Is it economical? Okay. And then the other thing, what is important is that does it meet the requirements of the study objectives? Because before even moving out to do any survey, you have to ensure that your objectives are set right. So, and it's from your objectives that are the ones that they give you a roadmap on how to construct a good survey. So at the same time, this particular survey should provide reliable results. Okay, and then when it comes to sampling issues in the survey, it is also important to note that as you're moving out to collect, as you're moving out to get your sample size, it shouldn't be too low, and then it also shouldn't be too large. But still, as we move further, we are going to see how can you determine a sample size of your study. So, and we also should have to ensure that the sample size, that the sampling procedure that you are using should give you the best estimate that you want to consider for your study. It has to ensure that it provides to you a minimum error. In that particular case, you'll be able to come up with an unbiased estimate, as well as the economical consideration. Because most of the time, if you're looking at conducting a very big survey, and you have to look at issues of money. Is it economical that I go in for this, or I should opt out and maybe reduce on my size and do something else? All right. So the main objective of sampling theory, actually, when it comes to sampling, the various attributes that you need to note at the back of your mind, that you need to ask yourself, that is it economical? Can it be easily implemented? Do my attributes by the end of the day give me unbiased estimates? And then also minimizing the sample variation. In other words, you need to reduce the variation within or among the attributes, which is also very important, because by the end of the day, as you move out, these attributes have got the variance between the attributes is different. So how are you going to ensure or to see that you produce less variation as you can? So now let's move on to the methods in simple surveys. So we are going to start with a simple random sampling. As far as sometimes it is abbreviated as SRS. So in most studies, people employ the SRS, that is the simple random studies. Okay, and well, it is the simplest among the sampling choices, and whereby what we consider in this particular case, that each element within each element has an equal probability of being selected from a list of all population limits. So you want to get your n, the small n or the little n, that is the small n from the entire population. But the point is that, or the assumption under the SRS is that every element has an equal chance or an equal probability of being selected from the entire population list. So as we move on, of course, by the end of the day, what you're supposed to have at the back of your mind is that every procedure that we are going to take, it has got an advantage at the same time a disadvantage. So now when you look at this example, the diagrams that I'm showing here, we are saying that with simple random sampling. So you can pick this one, and then also from this particular list, every individual has an equal chance. You can pick this particular person here, or you can pick this other one, or whoever within the population. The assumption is that every participant has an equal chance of being selected. So that is the advantage that it has within, if you're considering a sampling frame for the whole population. though it is one, as I wanted to discuss about the disadvantages, but I'll look at that later. And then we see how can we compare it with also other methods that can be used in the sampling procedure. We also have another type that is called systematic sampling. So according to Levy and Lemshaw, that is in 1999, they're saying that with systematic sampling, either by itself or is a combination with some other method, may be the most widely used method of the sampling. But what we have to note at the back of your mind that any procedure that you're going to use, it depends on the objective of your study and what you want to achieve at the end of the day. So yes, they are saying even Kish 1965 agrees that it's a mostly sampling procedure that is being used, and it can also be an alternative of the random sampling. But by the end of the day, we're going to see that still with you can perform a systematic sampling procedure and you still continue to do a random sampling. So how does that work? Let's take an example. Most of the time when it comes to a systematic sampling procedure, you pick the first unit at random, because I mean, you do not have a specific procedure that you're going to use. The first unit that is picked or the first observation that is being picked is selected at random. But then the next units that are being used, they are selected according to a predetermined pattern. So most of the time, what we want is that from the entire population, call it N, we want to get a small sample that will be able to give us a clear representative of the entire N. So we need to get what we call a systematic sampling interval. And how do we get it? So what we do, you consider your first limit. The first unit is selected the first unit is selected at random, and then from a sample, let's assume that you're starting from 1 to k samples. So for us to get a systematic sampling unit, what we do, you get the capital N, that is the population size, and then divide by small n, that is the sample size. And your k will give us the systematic sampling interval, implying that after selecting your first unit randomly, then the interval you'll be just adding it on your first element, and then it gives you, for example, if it is nth or if it's kth. So you'll have to pick at every kth element, and then it is one that you'll include in the sample. Okay. Now let's take an example. So assuming that you've got a population of N that has got 100 observation, and then you want a sample size that is equal to 10. So your systematic sampling interval will be, we say that it's K, which is 100, capital N over the small n, and this is going to give you 10. So for example, when you look at this one, you're looking at, you need to select a start, where you're going to start from. So if you're going to have from 1 to 10, remember now you're going to pick every 10th, okay? So you can pick any number in between. You can select pick randomly any number between 1 and 10. It doesn't matter where you start from. But what is important is that all the numbers that are going to, all the other units that you're going to include in the sample, then they have to take that particular interval, all right? So in this particular case, remember I said my sampling unit in this case will have 10. So if I say I take 7 as my first, if I take 7 as my first element, okay? So I'll have 7. So, but remember the interval is 10. So it's implying that the next person or the next observation that I'm going to include in my sample size, so it has to be 7 plus 10, which will be 17. Then the one that will be in that, when I add 10, I get to 27. So that will be in the 27th position. That is the person I'll include in what? In my sample, until to when when I get the sample size that I want. So in other words, this is just the generalized formula. So the point is our K is equal to capital N, that is the population size. Then you divide by N, that is the small n is the sample size that you want to use in your study. But then, so the question could be, what could be done in case your K is not an integer? Because by the end of the day, when you're selecting different observation, okay, let's say that you're selecting the observation are just individuals or respondents, you cannot have points. So what happens in that case? So if we consider another example, which is 175, that is, if you want your n to be 175, and then your total n, the capital population size is 1,000. So your K, when you divide, you're going to come up with 5.71. And remember, so in this particular case, what you can do, the solution, one of the possible solutions that you can do, you can either take 5 as a whole number, or you can round off and take the next number. So in this particular case, you have you can either pick your K as 5. Okay. You can either pick your K as 5 or as 6. So then it implies that now this one is going to guide you on now what n you are going to choose. So if you're having your, now in this particular case, if I'm considering my n again, which is 1,000, in case I divide by 5, then it implies that when K is equal to 5, I'll need my n to be 200. And when my K is equal to 6, I divide by the total, my capital N, then it implies that if I'm to take my sampling, my systematic sampling interval 6, then I will need my n to be 167. Okay, maybe just a quick one. Somebody was saying that I explain the margin of error again. Like I mentioned earlier, that the margin of error, it can be the same as the sampling error. Most of the time, when you're considering, when you're picking a sample, you want the sample that you pick to give you a true presentation of the entire population. But as you go ahead to do this particular sampling, well, I mean, if you're doing, you expect a certain error, it's not going to be a perfect representation. So it is what I'm referring to as an error, or you can call it a sampling error, or you can call it a margin of error. So these words should not confuse you. So because by the end of the day, like as we'll move on into, we're going to discuss about the regressions and so on. So like you can fit a model, but still you get an error. So in this particular case, like I said, you go into sampling, since not all the elements are selected from the entire population. So by the end of the day, we anticipate that an error, a small error or errors are bound to happen. But the point is that how can we make sure that we minimize them? So let me ask in the chat. Have you gotten the meaning of the margin of error or sampling error? Okay. All right. And then when it comes to the cross-sectional surveys, like I mentioned earlier, when it comes to for the case of the cross-section surveys, this is usually, you perform a certain survey, you do it at a particular point in time, and then it ends there. Let me give a particular example. Assuming maybe you're going to go to the field to collect your data, okay? Maybe you're going to ask you about farmers, about their perception of the new cassava product or a new cassava brand that is on market, and you want to get their views or ideas on how they perceive it on the market, whether it is doing well or it is not doing well. That one, and then after getting their ideas, you use them to make an informed decision. The survey is completed, and you use what you've collected from from the respondents to come up with conclusion. So that in that particular case, it will be a cross-sectional survey. You conduct it at one point in time, and then that is ended. That's why I mentioned that when you look at most of the studies that are being conducted, especially by our students, they're like, okay, I'm going to do my thesis. This is my topic. That's what I'm going to look at. They go out, they collect data, they answer, they come and write the thesis, they submit, and then that is finished. So you use the results that they have gotten to come up with conclusion and recommendations. So it is what we refer to as a cross-sectional survey. Okay, let me ask again in the chat. Is that also okay? Right. Okay, that's fine. Great, let's continue. So we had moved on to, I was still explaining about the systematic sampling approach. Like I mentioned earlier, as we move on to discuss, as we are discussing, try to picture out, in case you're doing a particular study, which sampling procedure would you think would best suit your study? All these approaches can be applied in either agricultural economics and experiments and so on, because by the end of the day, sampling, you cannot run away with sampling in case you want to collect data. All right. So when you're using, when do we use a simple, when do we use a systematic sampling? Of course, like I said, it all depends on the objective that you want to achieve, but most of the time it is preferred over the simple random sampling. And when you don't have the list, when the population list does not exist. So in other words, you're not so certain of the big population, and you can still use it as well when you're using a small area. Okay, so this is what I was referring to when I was talking about the kth, somebody in the kth position. So assuming that this is our sample, all right, then you pick the first observation randomly. Okay, so in this particular case, from the diagram I'm showing, they are picking after every 2 persons. Okay, so when you pick the first one, so it implies that your sampling interval, the systematic sampling interval in this particular case is 2. After the second observation, you choose the one in the sampling list. You take that person, that particular position. So here you choose the first one, you count 1, 2, you include this person in your list as part of your size. You count, then you skip the second, the 2 people, then you go on to, you pick the one that gets in the other position, and so on. So also, let's assume that maybe you're conducting still a telephone interview, or you've got a list of students that were admitted, and you want to carry out a certain survey. Or you've got, different plot names, and maybe you just want your sample size to be n. All this can be generalized to other procedures. So in this particular case, I've got, for example, like my total n is 100. That is my population size. But within this population size, remember that we cannot go in for the entire n because of it is expensive. You cannot go around getting every respondent. However, we can use a sample from 100, and then we are able to make a conclusion that, or like we called inferences or conclusions for the entire population, assuming that we want our n to be equal to 20 in this particular case. So how are we going to get the systematic sampling interval? It's going to be n out of 20, and this particular case, it's going to be 5. So if my k, that is the systematic sampling interval, is 5, so between 1 and 5, I can choose any number to start with. It doesn't matter, but provided it's between 1 and 5, or between 1 and the systematic sampling interval that you've chosen. In our case here, it is 5. So in case I start with 4, okay? if I start with 4 here, then it implies that, so I'm going to count, and then when I reach to the 5th, so I'll pick that person and consider and put him or her within my sample. So if this one is my first one, I'll count 1, 2, 3, 4, 5. So when I get to the 5th person, I'll include that person in my sample. The same case, I skip the ones in between. I take the ones after every 5th. So I pick the 5th person each time I count, the one that belongs in that particular position. So assuming you're conducting a telephone interview and you've got this list of 100 people, you can still go ahead and use systematic sampling by saying, well, I'll use after every 5th person, I'll include that person within my sample size to be among my sample size. So by the end of the day, as you move on up to 100, you find that within your sample, you'll include up to the 99th person that will be in this particular position for you to come up with your N to be equal to 20. Okay, so like I said, if you start with the 4th, that in case that is what you've chosen, so you'll take every 5th person or every 5th element or unit, whatever term that you're calling it. Okay, let me ask in the chat if we are on the same page. Are we on the same page? Okay. All right. Now let's move on. We've seen simple random sampling. We moved on to systematic random sampling. Now, what about stratified sampling? Okay, maybe I should also bring this to your attention that most of the time, especially when you're doing surveys or you're writing a publication, there is a section whereby you need to explain, or the reviewers will ask you, what sample size did you consider? How did you get to the particular small n that you're using this particular study? And it is always important that you have to really come out clearly to explain how you determine your sample size. Of course, for you to come up with a sample size, you have to first have different sampling procedures that now we are looking at, which you still have to explain in that particular section, such that somebody can easily fall through what you're saying to see that, like, yes, using this particular procedure or sampling procedure was able to come up with the stated sample size. So let's move on to stratified sampling. So as far as stratified sampling is concerned, in this particular case, the population is partitioned into groups, okay? And these groups are called strata, okay? And the sampling is performed separately within each particular strata. So what is important, what should keep at the back of your mind is that there is partitioning into groups, and then the partition groups are called stratas, and at the same time, the sampling is done within each particular strata. Within each stratum, the stratum is in full. Strata is a single, then stratum is the plural. So within each stratum, then a sampling is performed. Let's take an example. We should note at the back of our mind is that when it comes to stratified sampling design, the stratum variables are mutually exclusive. In other words, they do not overlap each other, or they are disjoint in nature. For example, you can say, I'm going to look at a place of residence. And this particular case, I'll look at considering the rural, the urban, and then the rural areas. So implying that my strata will have those who belong to the urban area and those who belong to the rural area. Or you can take an example about economic categories, those that belong to those with low income, middle income, and then those in the upper income. You can consider also geographical locations, like maybe you can say the east, the west, the north, and so on. You can look at, you can talk about the sex. In this particular case, you're stratifying the males separately from the females, then the race, or you can call it ethnicity. So in all these stratums, the point is partition these particular groups, and they should not be an overlap. So they must be mutually exclusive. And what is important is that as you are stratifying, for example, if you're considering urban and then the rural, okay? So we need to, the population within, the population should be homogeneous within a particular stratum. Within, for example, when you're considering the urban setting, or for example, let's talk about sex. If you're considering females and then males, let's say if you're looking at first year students that have joined, the sex of first year students, we are having the males and then the females. So most of the time with homogeneous, maybe you can say they're around the same age, or maybe they've got similar expectations and so on. So that is they should be as homogeneous within a particular strata, okay? And then, but they should be, the population should be heterogeneous between the stratas. One, for the case of the sex, that is, we have homogeneous, they're all females, homogeneous, they're all males. And with heterogeneous, we are looking at between stratas, whereby we are looking at the one of the females and then the one of the males. So there is homogeneity in that particular case. So the point is, we are noting that these stratums should not overlap each other, and then we are looking at the partitions within the groups that we are considering. So when should we apply the stratified sampling? So sometimes we can apply this when the population groups may have different values for the responses of interest, and you want to really understand maybe the interests, and you want to compare the interests of the females and then the interests of the males. And by the end of the day, you can even compare them and see how different they are. Or sometimes you may want to improve on the estimation from each particular group. As we move on, we're going to look at the probability proportional to size. So it can also still help us when we are trying to get to improve our estimation from each particular group that we have stratified. And we also, when you want to ensure that we've got an adequate size for each particular group of interest we are trying to consider. All right, so and this is just a particular example. So like I mentioned earlier, you're trying to put them, you're trying to partition them. Let's assume that maybe this is a group of what example can we take? Okay, well, when you consider that these in this particular example that I'm showing, and you're trying to put them into particular groups, you're stratifying them. In other words, you're partitioning them into respective groups, and then thereafter you can come from each particular group again to pick to do a simple random sampling that you want to consider in your general population, or in what you want to consider as your sample size. So the point is that the principal objectives, if in stratifying, again, like I mentioned earlier, you want to reduce the sampling errors. So under my time is up. I stopped. Okay. Okay. Okay, fine. Okay, let's finish with sampling. I'm seeing a lot of comments that people are tired. Okay, let me finish the part of sampling, then I'll end there. Maybe we'll start from there tomorrow. So we've got, there are two basic rules for stratified sampling. Like I mentioned earlier, that from the stratified groups, you have to ensure that at least a minimum of 2 elements must be chosen from each strata. At the same time, the population should be homogeneous within each stratum and heterogeneous between the stratas. Okay, let's look at the cluster sampling, and then we will summarize. When it comes to, remember we stratified, I said is that you partition the respective groups. Like we said, when you look at sex, you partition and look at the females and then the males alone, or when you're looking at a place of residence, you can consider urban and then rural. But when it comes to cluster sampling, in this particular case, usually what happened, a cluster is just a group of population elements. So, and this particular cluster or this group, it consists your sampling unit. So now in this particular case, instead of considering a partition, we don't do that. We just take a certain group. So a certain group of a population. So within cluster sampling, the clusters are the first sampling units. Let's take an example. In case, for example, you're dealing with different schools. So each school can act as a cluster. Or when you're working at universities, then each university could be a cluster that you want to include in your sample. So this is an example that we can look at. Cluster sampling, assuming that this is your cluster population, okay? For example, you've got a 1, 2, 3, 4, 5, and then 6. And then from this big population, you want to consider only 2 clusters. You can choose and say like, no, I'm not going to consider all the clusters that I have. For example, let's say if they were schools, and if you've got 10 schools, but among these 10 schools, which are your clusters, you can decide and you can do a simple random sampling and say, among these 10, I'm going to consider only 2 clusters, and then you include them in your study. But in case you pick the clusters and you consider all the elements within those clusters, then we refer to that as, I've explained that. Let me first look at the primary sampling. I've talked about the primary sampling units, the clusters, that is which I mentioned here, that a cluster are the first sampling units. So primarily in the sense that the ones that are first picked, they are the ones that are first selected. When you, for example, if you're looking at universities and then you consider each university as a cluster, so that will be they will act as your primary sampling units. So, but still after that, after getting your clusters, you can go ahead and do either a systematic random sampling or a simple random sampling, depending on what number that you want to include. And from the primary sampling unit, you can as well go ahead still and do secondary sampling. You can as well move on and have a secondary sampling units. In this particular case, from the clusters, you go further and again do simple random sampling or systematic sampling, or you can, and then the clusters that you've chosen, you again within them, you do another simple random sampling. So the sampling units that you'll get after the second time, refer to them as secondary sampling units. Okay. Like I said, when it comes to simple one-stage cluster sampling, so in this particular case, you have a list of your clusters. The moment you select them for the first time, that is with a simple random sampling, and you consider all the units within those particular clusters, we refer to that as a simple one-stage cluster sampling. And then we also have what we call the simple 2-stage. So in case after you select you first select the clusters by simple random sampling, and then you select again within the clusters that you have the second time. Okay, so, and you pick the various elements that you want to include within your sample size. We refer to that as a simple 2-stage cluster sampling. So, and then lastly, I want to conclude, we have a multiple stage sampling. So with the multiple stage, it involves everything. It involves stratified, it has got cluster, it has got simple random sampling and systematic random sampling. So that is a multi-stage, whereby you're looking at, most of the time it is used when you're looking at the national level surveys. Most of them are performed using a multi-stage sampling design. Sometimes they first get clusters, then after getting the clusters, the clusters are stratified. After them being stratified, somebody can use a simple random sampling or a systematic random sampling. So the example that we can take, like I explained earlier, you can use a region. Okay, maybe you're considering regions, but within the regions, it is a nested approach. So within the regions, you can say it is very big. Now let me go ahead and pick the districts within these particular regions. But still, you find that when you're looking at the district, it's still a big sample. You narrow down and move on to the villages, but still within these particular villages, then you can do systematic sampling or simple random sampling, and then you move on to the households. So all that procedure, when you look at that procedure, all the different sampling approaches are involved. So in that case, that is what we refer to as a multi-stage multi-stage sampling. So it combines all the several sampling procedures depending on the situation and at what level do you want to achieve your sample size. Cluster. Okay. There's a question that I differentiate between stratified and then cluster. So I mentioned that when you come to stratified sampling, okay, with stratified sampling, in this case, you're trying to make partitions within a group of a population. For example, in case you're looking at the sex of, you're looking at sex. If you're considering sex, for you to stratify, it's like you're putting it in various levels. Like you're going to consider, you're looking at sex, you're going to consider the females separately and then the males separately. Because by the end of the day, you might find that the opinions or the perceptions that these people have towards your questions of interest are different. So you first get the opinions from the females and then get the opinions from the males. And at the end of the day, you can make a comparison and come up with a defined conclusion. So other example that you can look at, I talked about the place of residency. Maybe you want to check the standard of living among the people that live in the urban areas and then those that live in the rural areas. So in that particular case, you can use a stratified sampling. But at the end of the day, you want to pick an idea on people's standards of living between the different places of residence, either urban or rural. Whereas when we come to clusters, we are considering different groups within a population. The example that I said is that, let's take an example of schools. Each school can act as a cluster. Maybe you want to look at how the performance of national exams maybe in schools. And so you can say we are going to pick various schools in maybe within the central region. In case, for example, each school will act as a cluster. For it, you just pick groups of, you just take it as a group. And in case you're going to consider all elements within each cluster that you've picked, then it implies that you're looking at the first stage of cluster sampling. But in case still within these particular groups or the clusters that you've chosen earlier, then in that particular case, you'll be looking at simple two-stage cluster sampling. So with stratifying, you're looking at layers, or you're looking at partitions within a particular group. Whereas with cluster sampling, you're considering a particular group to be a cluster. And then it's from within that cluster that you can further go and do either you can, maybe in case you've got like 10 groups or 10 clusters, you can do simple random sampling and pick like 3 among the 10 clusters to be considered in your study. Okay, let me ask in the chat. Is that okay? They're tired. You're tired. Okay. Okay, we are going to stop here for today, and then we'll